Okay, so hello, Jacob or Professor, whichever one it ends up being. My name's Tony. Hello. I forget how I did this the first time, admittedly, but I feel like it was probably smoother than this. Anyway, this is the solution to problem 2.41 in Griffith's Introduction to Electrodynamics, 4th edition. And here is problem 2.41. So they tell us that we have two large metal plates, okay? And I find it best to draw them immediately. Right, something like that. Or, well, let's see. Like this. Right, something like that. Right, we have two large metal plates. They each have area A, so area is some constant A. Right, and they both share it. And they're held a distance D apart. Okay, so they're spaced a distance D. Now, suppose we put a charge Q on each plate. What then is the electrostatic pressure on the plates? Okay, so we need to find, right, all of basically the areas or the spaces where the electric field is affecting each other of these two plates, right? So we know that in the simple case of something like this, right, where they're directly parallel planes, that E is going to be a vector, and its magnitude will be sigma over epsilon naught, and it's going to be in the n hat direction. So what the n hat direction is, or what it stands for in this situation, is the unit normal vector, or the unit normal direction. No, yeah, unit vector, unit normal vector. And by normal, what it means is that this unit vector is going to be perpendicular to the surface that is producing this electric field, right? And so what we have to find is we have to determine first where the n hat direction is. So in the situation of electric field, normally, right, if we have a closed surface, say we have a sphere, right, something like this, say we have a sphere and there's no openings on that sphere, well, we normally determine the positive n hat direction to be basically radially outside in this case, right? So it's pointing outwards. Outwards would be the positive n hat direction. But in this case, right, we have two surfaces that are in relation to each other in space, sure, but they aren't a closed boundary where we can easily define just based on outwards or inwards, right? So what we want to do is relate this to a Cartesian situation, right? We want to say this is like the x, and this is the y, and this is the z, right? And so we want to pick which direction we consider to be positive n, because the relation that they have will affect them similarly no matter what, right? It's as long as we have one direction being determined positive, then when it's negative, there won't be any issues in calculation, okay? So let's say that this is surface 1 and this is surface 2, okay? To begin, let's find the electric field on the inside. And again, we know that the electric field is going to be perpendicular to the surface, right? And so if we want to find the inside, we know that E1 is pointing this way, and we know that E2 is pointing the opposite direction, right? And so let's just say, for the simple sake, based on this Cartesian relation, that, which is not accurate, by the way, there wasn't a defined situation, but it's fairly simple to just say that, yeah, we're probably on we're on the X and Y, you know what I mean? We're on the X, Y, and Z's. So in this situation, right, let's say that the positive X direction is in some way proportional to the positive n hat direction. Okay, and so for E1, and let's say inside, all right, or well, maybe let's say between. E1 between is going to have magnitude of sigma over epsilon naught, right, which is the permittivity of free space. Might as well mention it. And then if we say that the positive x and the positive n are synonymous, right, then it would be going in the positive n hat direction, right? It's pointing towards the positive direction. And then we want to find E2. So E2 between is going to be sigma. It's going to have the same magnitude, you'd think, sigma over epsilon naught. But now it's going in the opposite direction while still being in the n axis, right? And it's going to be negative n hat, right? Which we can then just distribute this, and we find that it's negative sigma over epsilon naught n hat, okay? And so we want to find the total electric field on all sides of this, right? We want to find it out here, we want to find it out here, and we want to find it in here, okay? And so let's find that we're doing the between first, right? Let's find what that would be. So what you do is you just sum them. E1 between plus E2 between, okay? And that's going to be fairly simply, right? It's just going to be 0. And I'll write out, just for our edification here, that we have of the same exact magnitude, these electric fields, just pointing in opposite directions, which will cancel each other out. Okay, so E between, electric field between, is going to be 0. And now we want to do the outside. So let's start with the left here, right? Let's do outside S1. And the electric field from S2 is not going to affect it because it's not going to be able to pass through the conductor, right? So, well, surface 2 electric field will not be able to pass through the conducting surface of S1, right? So we don't need to worry about it on that side. So S1 is going to have E1, E surface 1 outward, okay? And it's going to have the same magnitude pointing in the opposite direction, right? But it's going to be pointing in the negative x hat, or again, in our case, the negative n hat. And I think right now I'll stop mentioning that, right? We just know they're synonymous. So it's going to be sigma, same charge density, over epsilon naught, excuse me. And it's going to be in the negative n hat. So this is the magnitude, or this is our vector E1, sigma over epsilon naught n hat. And then we want to find the other one. And I think, it's fairly simple, right? What it's going to be. They have the same area, they have the same sigma, right? And then they're going to have the same magnitude, right? Because they have the same charge that's been placed on them. So E2 out, right, which is right there on that side, is just going to be sigma over epsilon naught n hat, okay? And then we find, so now what we want to know is we want to find, right, because even though we're doing all this, we're still solving for something else. We're solving for the electrostatic pressure, right? And so the electrostatic pressure is formulaically defined, and it's a scalar value, right, as epsilon naught over 2 times E squared, okay? Now, there's an important distinction that needs to be made here, right? When we square E, we have E in a vector form, right? So if we're squaring E, what we're doing is the dot product of two vectors, which will result in a scalar value, which is why E doesn't have you wouldn't denote it in this electrostatic pressure formula as being a vector, because it's not now that you've squared it, right? So, and I'll show us how we do that. And I think it's important to note, to actually write and say what electrostatic pressure is, right? Because I feel like I had no idea before I began, and feels too interesting to leave out. So imagine we have just a different surface, exact same values, right? And everywhere on that surface, it's projecting, the electric field pointing out like this, right? So this surface has charge. So it's surface with some charge, not surface of charge, surface with charge. And it's going to produce an electric field, right? But that electric field is then in tandem going to produce a force on the surface, and it's that basically it wants to pull the surface that is producing the electric field in the direction of the electric field. So it's almost pulling itself in a way, right? And that thing that it's producing, right? What is produced is an electrostatic pressure. Okay, so that's what that is. It's important to know what that is, I think, to be able to solve it with confidence. So then we're going to solve that. So let's find, first of all, E squared, right? And I'm going to put it this way. So this is effectively E dot product, right? So you might be able to see it immediately, right? But if I dot something, right? If I dot something with itself and it's negative, I'm going to be multiplying two negative components, right, together, and they're going to cancel out, right? The negative is going to cancel out, not the components. So the negative is going to cancel out, and so it'll be positive. And if I do it with two positive, single component vector fields with two positive, exactly the same, components in that individual one, right? Then it's going to give me the same output. So I should mention that E squared for one outside is going to be equal to E squared for two outside, right? Because of that, just because you're squaring a negative, right? So you'll get the same result. And because they have the exact same charge in the exact same area, and that's what matters, okay? So we need to know what sigma is. And sigma just means charge per unit area, right? And so that's going to be the Q that we put on the surfaces over the area of the surfaces, right? And then we now know, so let's do, so we're going to do it here. We have E dotted E, and that's going to give us sigma over epsilon naught n hat dot sigma over epsilon naught n hat, right? And then we're going to replace our sigma values, right? And actually, we can just sort of distribute them out immediately, right? We've got sigma 1 times 1 over epsilon naught, right? And it's n hat dotted n hat. And if you take the dot product of two unit vectors that are parallel, right, this is going to give you 1. So this goes away, maintaining the function while going away. And then we replace our sigma with what we found it to be, and we have Q, right? And it's important to see here now that this is all squared, right? And so we have Q over A times 1 over epsilon naught, all squared, equals Q squared over A squared times epsilon naught squared. Okay? And that is equal to E squared. Okay? So then we just plug this right back into our electrostatic pressure formula, right? We have pressure is equal to epsilon naught over 2 times E squared. And we get epsilon naught over 2 times this, right? Q squared over A squared over epsilon naught squared. And the only thing that changes here is these go away, right? And we end up with a pressure, electrostatic, that is equal to Q squared over 2A squared epsilon naught. Okay, and that is the solution to 2.41 of the 4th edition of Griffith's Introduction to Electrodynamics. Thank you for your time. Have a good one. Bye-bye. I can just...